In this video, we are going to explore the concept of work. First, let's go through a few simple examples, and then we can define what the work is in general. So first of all, if you have a force acting on an object, and that object changes its position, then you can define a concept like work, and roughly speaking, work is the force times the displacement in the direction of the force. So the classic example that one uses is the movement of a bead on a wire. Suppose you have a bead and you have a wire going through the bead, so the bead can only move from point A to point B along this straight line. So let's say you have the particle initially at position A, and the force acting on the bead is given by F. Sometime later you have the body here, and let's say for simplicity's sake, at this point here, once again there's a force acting on it. It's the same force F, okay, the same magnitude and same direction. And then some more time later it's moved a little more towards B, and again for simplicity's sake you've got a force F acting on it in this direction. So what's the work done by the constant force field F? So the word field is being used here because at each point on the particle's trajectory there's a force acting on it. So there's a force vector associated to each point. Never mind that for now. So you notice that the displacement is always taking place in the direction of force. So you simply have, if you apply this basic idea, you have work done equal to W equal to Fd. D being the displacement, or the magnitude of this displacement, is a positive number, and the magnitude of the force is a positive number. So in this case, work done is positive. You have this positive Fd. At this point, I would like to recommend an exercise. So you can show that if the bead has a mass of m, and let's say its initial velocity was v1, vi at point A, we can imagine that if you apply a force in this rightwards direction, the velocity is going to change. Since the velocity vector is pointed towards the right, the velocity vector will keep increasing. So you see some time later the velocity increases if you have the force acting in this direction, and some more time later this force causes even further increase in velocity. Now you can show using Newton's second law that the final velocity is given by some Vf. Well, if the final velocity is given by Vf, you can show that half mvf square minus half mvi square equal to Fd, which is, well, you can think of this as the change in kinetic energy, and we showed, or we argued, that this is the work done by the force F. So this starts to give you some impression that the change in kinetic energy is somehow related to the work done, right? So let's work through this example. If you have a constant force F acting on this particle of mass m all the time, then you have the following acceleration on the mass. You have A equal to F by m. So this is, in this case, a constant acceleration because the force vector acting on the particle at each point is a constant. So then you can apply the following expression. You have Vf square equal to Vi square plus F by m times 2 times d. Multiply both sides by half m. You have half m Vf square equal to half m Vi square plus Fd. So we've proved this expression. You're starting to get an impression perhaps that the change in kinetic energy is somehow related to the work done. Alright, let's carry this example a little bit more forward. So suppose once again you have a bead moving on the wire. Let's say you have an initial velocity going towards B, You have this rightwards arrow, but this time you have a force acting in the opposite direction to the displacement. What's going to happen? So the particle is going to slow down, but it can still keep moving forward, right? This is just going to cause a deceleration. So you see at some time later the particle has moved some distance here, and again you have a constant force field here. You have a force acting to the left, but the magnitude and direction of the force is the same at each point from A to B, right? Now what will be the work done here? You notice that the force is acting in the opposite direction of displacement. So if work done was, roughly speaking, force times the displacement parallel to the force, this time the displacement is anti-parallel to the force, so you have to put in a minus sign, and the work done would be W equal to minus Ft. So in a similar vein to the exercise shown before, you can once again show, using Newton's second law, that in this case half mvf square minus half mvi square would be minus Ft. So once again the change in kinetic energy would be the work done. Okay, that's starting to seem like a common theme, right? Alright. So now let's suppose that the force acting on this bead, let's suppose once again the bead moves from point A to point B. We can call this, since this is a straight line, we can say the particle moves along a chosen x-axis in this direction. So the angle that the force vector makes at each point, right, as the bead moves from A to B, there's a force acting on the bead at each point, and the magnitude and direction of the force is constant, and at each point this direction is some angle theta above the x-axis. What would be the work done? Well, because roughly speaking work done is force times the displacement parallel to the force, we need to take the component of the force that's parallel to the displacement, and the component you can imagine is simply given by F cos theta. So the work done would be W equal to Fxd or Fd cos theta. You can once again show that the change in kinetic energy, or half mvf square minus half mvi square, would be given by the work done Fd cos theta. So until now we've been dealing with a very simple example. You have a bead traveling along a straight line, and the force acting on the bead at each point on the line has constant magnitude and direction. Let's complicate things a little further by considering cases where the magnitude of the force keeps changing as you move along this path. So a simple way to do that would be to consider the following case. Let's consider the example of a bead connected to a string. So when you have non-constant forces, you can imagine that an integration will be involved somehow. So recall that the force acting on an object due to a spring is proportional to the displacement or to the extension or compression of the spring from its equilibrium position. So the common way to take coordinate systems in this case would be to take the coordinate x equal to 0 at the equilibrium position of the spring, right? So this would be the coordinate system chosen. You have x equal to 0 when the spring is at equilibrium. If the spring goes a bit further to the right, then you would have f equal to minus kx. In that case, like let's say x equal to a is a positive number, and then the force would be pointed in the opposite direction, the force due to the spring, and its magnitude would be given by f equal to ka. So you have finally f equal to minus ka as a vector. So the question is, let's say you have the particle or the bead moving from point A to point B. Now as it moves from point A to point B, clearly the force on the bead keeps changing, right? The force keeps increasing. You notice that initially the force vector is given by f equal to minus ka, and finally the force vector is increased at B, and at some point in the middle it's something different. How can we find the work done in going from point A to point B? obviously you have to do an integration. So let's consider a small increment of path going from A to B. Let's call this dx. And you can imagine that the force acting on the particle as it covers this distance dx being very small, so the force will not change appreciably. So let's call this, let's say the work done in going this small distance dx would be given by F into dx. So keeping in mind the examples we worked out before where force was constant, we can just say in going this small distance, the force is of constant magnitude and it points backwards. So you have dw equal to F dx. The increment of work done is F dx, and then the force would be just minus kx, right? If this interval is considered at point x. Then what's the work done in going from A to B? Clearly you have to add up these incremental work done in going these incremental distances dx from A to B, and in doing so you just have to integrate. So just integrate this expression kx dx with keeping that minus sign in account. Integrate from x equal to A to x equal to B, and this integration gives you just minus half kx square. Evaluate at x equal to B, the final point, and at x equal to A, and finally you get the work done WAB equal to minus half kb square plus half kx square. So we've seen one way in which to generalize the concept of work. Starting from constant forces, we've seen that when you need to consider non-constant forces, you have to do an integration. Now let's consider the most general case. In the most general case, you basically have a particle going from point A to point B along some complicated path like this, okay, in 3 dimensions. Doesn't have to be a straight path, right, going from point A to B. And let's suppose when you have a particle going along this path, at each point you would have some force acting on the path. Now there is no guarantee that at each point the force would be the same. It could be different. It could have a different magnitude, and the force could even point in a different direction. But let's say going along this path from A to B, you know the force acting on the particle at each point as it goes along this path. How would you find the work done by this force field? And now you see why it's called a field, because you have a force vector at each point on the path, right? You have a different force vector at each point on the path. How would you find the work done due to this force field in going from point A to point B? So you say that let's consider a small section of the path. Let's consider going from just this point to this point. The displacement vector from this point to this point is clearly given by this dr. And let's say we know that the force acting on this small increment is given by F. Because this increment is very small, this dr is very small, let's say it's safe to assume that the force remains constant along at least this small region of the path. Then you can say that the infinitesimal work done in going this small displacement is given by dw, and then you can use the basic idea of work done, which is displacement parallel to the direction of the force. So you take the parallel component of force to the displacement, you use F cos theta, so you have dw equal to F cos theta dr. Now F cos theta dr should remind you of basically a dot product, right? Because F dot dr is just F cos theta dr. So basically dw is given by F dot dr. Then the work done in going from point A to point B is simply given by the integration of dw going from point A to point B. So finally you have a solid definition of work done. The work done by the force field F in going from point A to point B along a given path is the integration of F dot dr along this path. And this is sometimes known as a line integral, because you're integrating over the line going from A to B. This given line, okay? So this is a line integral. You can imagine that in general this is a rather difficult thing to do. You have a complicated force field and you may have a complicated path going from A to B. In the next set of lectures we shall see some special cases where this work done is very easy to compute for various reasons. But we appreciate that in general this is a formidable mathematical task.